Okay, good afternoon guys. This is Professor David J. De Los Reyes. I will be having a new topic. It's already this afternoon, it's past 12, okay? This will now be a topic on differential equation, variable separable. We are on the application of a differential equation, variable separable. This is in the computation of air pressure at any height in this world. Okay, let's proceed. This will now be lesson number 14, DE 14, on my channel. The course is actually differential equation. The subtopic is variable separable. This will be the computation of air pressure at any height in this world. Okay, I will try to read the problem. The differential equation containing the atmospheric pressure P with the elevation H above sea level is WdH plus dP equal to 0. We are given this equation here. Okay. That's according to the problem. Where W is the density of the air at the height h. If the atmospheric pressure is 14.7 psi at sea level and 10.1 psi pounds per square inch at 10,000 feet above sea level, the question is, determine the pressure at 50,000 feet on the assumption that Boyle's law pressure is equal to kW holds. This is Boyle's law. And according to the problem, the variation of pressure with respect to height is this differential equation here. The problem gives us this differential equation plus the condition, okay, that Boyle's law will be used in the solution of this one. Boyle's law is actually, I think this is under physics or thermodynamics. That is, pressure is equal to K times the W, where W is air density. Okay, we are not interested on W. We are interested on the pressure at any height in this world. Okay, the given conditions are these. At sea level, on the level ground, the pressure is actually 14.7 pounds per square inch. At 10,000 feet above ground, above sea level, the pressure is 10.1 psi. So as you notice it guys, as we go higher, the pressure is decreasing. That's why in the airplanes, okay, at 30,000 feet, okay, the pressure is actually too low, and actually the inside of the airplane is actually pressurized. It was pressurized to be, I don't know, it could be 14.7 maybe, 14.7. But the airplane will not explode because it was totally encapsulated, you know, with a thick glass. Because just in case it will rupture, we are all dead. That's why the pressure inside the airplane is actually pressurized. Because at 30,000 feet, maybe, okay, the pressure is actually too low. And our body might explode. If the pressure in our surrounding is too low, we might explode. That's why the airplane, the inside of the airplane is pressurized. Okay, let's proceed. The question is, at the height of 50,000 feet, what will be the pressure? We now know, guys, that airplanes are pressurized because above sea level, the pressure is too low. That's why in the moon, there is no more pressure, right? So if you just move a little bit, you will fly. Okay? Because there's no more pressure surrounding you. The pressure is a negative pressure already. Maybe the pressure inside your spacesuit is maybe greater than the pressure outside. That's why if you move a little bit, you will fly. Okay, let's proceed with the solution. The figure is something like this. At sea level, the pressure is 14.7 psi. That's the normal pressure, okay? At 10,000 feet above sea level, the pressure is 10.1. It is decreasing. At the problem is asking at the height of 50,000 feet. It seems it's just the height of maybe an F-16 flying at 50,000 feet above ground. What will be the pressure? So if you notice it guys, the pilots inside the F-16 or F-15, something like that, is actually using a spacesuit and they got the oxygen mask. Because just in case they are 50,000 up and there's a leak on the airplane, okay, your air will be sucked and you can breathe. That's why they got the oxygen mask. Okay, let's try to solve the problem. For the solution of the problem, we will start with Boyle's law. This is Boyle's law. The problem gives us this equation here. That is, pressure is actually equal to K times W. We'll try to solve for W, for the air density. W will be equal to pressure over K. We do not know the value of this K for the meantime. We call this equation number 1. The other differential equation given by the problem is that the air density times dH plus dP is equal to 0. Actually, the problem gives us this differential equation here. Okay, so we will try to get the value of W from equation number 1. We put it on the given differential equation given by the problem. Okay, so what will come out will be W is actually P over K, right? So this should be P over K times dH plus dP equal to 0. Multiplying all terms by K. Okay. First one, this will cancel. So what will come out will be PDH. Second one, okay, it will be K times dP. So this is K times dP. And 0 times K will still be 0. Algebraic manipulation, KdP equal to negative PDH. Okay. Then we'll try to separate the variables now. This is now the resulting differential equation containing pressure and altitude. Okay, we got the constant, but later on we will solve for the constant. So if we try to use algebraic manipulation, we'll divide this or, okay, we'll move this one underneath. Okay, then we'll place this one on the left. So what will come out will be dP over P is equal to negative 1 over K times dH. We separated the variables already. That's why the topic, differential equation, variable separable. Okay? It is a pure constant pressure on the left-hand side. On the right-hand side, it will just be simply H or dH. So proceeding with the integration, the integral of dP over P equal to the integral of negative 1 over K times dH. We are now integrating. Okay? We already produced the required differential equation before the so-called integration. So integrating the resulting equation, left-hand side will be under natural logarithm. So this should be the natural logarithm of pressure equal to negative 1 over K. The integral of dH is just H. Okay? So after the integration, there should be another constant of integration. This is plus Q1. Right? We will try to compute for pressure as a function of H. Right? But unluckily, the pressure is actually with the guard. It got a natural logarithm thing. So to remove the natural logarithm thing, we will take the antilog, the counter antilog of that one, and the proper writing of this one will be e raised to the natural logarithm of P. We are taking the antilog of both sides to eliminate the natural logarithm, equal to e raised to negative 1 over K times H plus K1. E to the natural logarithm of P is just P. The antilog of the logarithm of any given function is just the given function, right? So P now will be equal to the right hand side. We will let e raised to K1 to be K2. So P now will be equal to K2 e raised to minus h over K. That is our general solution. We are now given pressure as a function of K2, as a function of K, and as a function of H. Don't be bothered with the value of K and K2 because later on we will solve for it. So, because our strategy is that we will solve for the pressure as a function of H with the value of K2 and K1 known. Okay, let's continue. Let's try to compute for the constant of integrations. We are to given initial conditions. This is the first initial condition and this is the second. So actually we could compute for the constant of integration. At h equal to 0, at sea level, the pressure is 14.7. Okay? We will substitute this 0 here and 14.7 back here. This should be 14.7 equal to K2 e raised to 0. But this is 1. Because minus 0 over K will still be 0. So this will become e to the e to the 0. And any number raised to 0 power is actually 1. So K2 times 1 is just K2. Therefore, K2 is actually 14.7. Okay? So we now know the value of K2. So the partial general solution, it will be K2, which is 14.7, a raised to minus h over K. Partial. Because for the meantime, we do not know the value of K. Okay, let's try to compute for the value of K. At a height of 10,000 feet above ground, the pressure is actually 10.1 psi. It decreased, right? That's why I told you, when we are on the airplane, the pressure surrounding the airplane is too low. That's why the inside of the airplane is pressurized. Okay? So substituting these conditions here, 10.1, we are following this, equal to 14.7 a raised to minus 10,000 over k. Okay? Therefore, a minus 10,000 over k equal to, if we divide 10.1 by 14.7, this should be 0.687. Right? And luckily, the unknown k is actually on the exponent. So to compute for the value of k, we will take the natural logarithm of both sides. Right? If we try to take the natural logarithm of both sides, it will become 10,000 over k, the natural logarithm of a equal to the natural logarithm of 0.687. This is 1. Therefore, we could compute for the value of k now. We can take for the natural logarithm of this one, okay? After the simplification, the value of k will be 26,645. It will be a positive thing because the natural logarithm of this one is negative and this is negative. So what will come out for the value of k will be 26,645. So the relation of P now, pressure, atmospheric pressure as a function of height, will be equal to 14.7 e raised to negative h. I'm following this. Over the computed value of k, which is 26,645. This is actually an exponential equation. But unluckily, it's an exponential equation that goes down to the first quadrant. Okay? The graph is something like this. Because as we increase the height, the pressure going up is actually going low. So the graph is something like this. This is the x-axis, this is the p-axis. We graph on the Cartesian, we make the altitude as abscissa and the pressure as ordinate. So the graph will be something like this. Okay, let's try to compute for the unknown. The unknown is actually at a height of 50,000 feet. That is the height maybe of an F-16 flying to attack somebody. Okay, what will be the pressure? We are given the relation. So pressure now will be 14.7 a raised to minus 50,000 over 26,645. This is 14.7. 50,000 over 26 is almost negative 2 or negative 1.8765. Since the exponent of a is actually negative, the value of this should be a fraction. Okay? So this will become 14.7 times 0.15331. If this was positive, the value should be greater than 1, but since this is negative, it is 0.5131. You could use your calculator, guys. Where is my calculator? It is here. Okay. You just display 1.8765. You place the proper sign negative, then press e to the x. Right? What will come out is this one. Using a scientific calculator. It should be a scientific calculator. You cannot use the basic calculator with only plus and minus. It should be a scientific calculator. With the sine, cosine, natural logarithm, common logarithm. It should be a scientific calculator. Or what will come out? 14.7 times this. The pressure at 50,000 feet is 2.25 psi. It's too low. Because if the pressure inside our body is something like, assuming it's 14.7, and you are at a height where the pressure surrounding you is 2.25, you will explode. Right? That's why the inside of the airplane is actually pressurized. The pressure at 50,000 feet, the pressure is 2.25, and the graph is this. Okay, that's the importance of differential equation. So we now know, guys, why airplanes are pressurized when we are above sea level. Because if the airplane is not pressurized, we will all explode inside the airplane. Okay, good afternoon, Los Angeles.